So we've been talking about the importance of data to lend objectivity to science, both in the philosophical sense that we think in science that there's probably some objective reality out there that we can characterize that's independent of our perceptions. We've seen operationally how important data are to science in terms of describing the facts of our experiments to make sure that we can distinguish between those things that are objective about what we've done versus our interpretation of those in making our conclusions. So these data really represent the pivot point between our deductive reasoning and our inductive reasoning in the cycle of science. So if data are that important to objectivity, then we better be able to put our data into some sort of objective context that we all agree is independent of our whims. The way that we do that is through the establishment of what's called reference frames or frames of reference. These are made famous in that they're really important to understanding Einstein's special theory of relativity, especially in terms of space-time type reference frames. Reference frames have expanded to have components that are beyond that, and we call those components dimensions. You're probably familiar with the term dimension in terms of 3 dimensions or 3D and the 3 dimensions of space, but there's also the dimension of time, and we also expand on this idea to say there's dimensions of mass, of energy, of force, all of these things that help us all agree on what numbers mean in a given reference frame. So the way to get started on this, I think, is to work with a basic number line or an axis on a graph. And you can think of an axis first being labeled with some variable that you want to plot on that axis. In this case, I'm going to call that variable x. And then in terms of this particular axis, I want it to represent a particular dimension in space. And we can do that by using the fundamental dimension that we call length. So you'll always see me represent dimensions in square brackets and with a capital non-italicized letter. We'll talk later about how that's important to keep dimensions distinguished from units and variable names. So we can say this particular axis represents a location along a line in space, and that dimensionality is characterized with the fundamental dimension of length. Now notice that I know a whole lot about what this axis represents before I even put numbers on it. So that's the beauty of dimensions, is they don't depend on any kind of number system or any particular units. You can still talk a lot about what a given variable means without having to know those things. Now, of course, if we want to measure things, we do want to put numbers on things. So we might have ticks on this axis that have numbers on them. And really, those numbers aren't very useful until we know what the units are. That's why it's always pretty important to put units on this axis. Now, there are many different unit systems that could be applicable here, right? We could have meters, feet, furlongs. There's way more than that. There's all kinds of different units for a given variable of length. That's another beauty of dimensions, is you can talk about the meaning of a variable without caring about those numbers or all of those potential different units that it could be. Because a lot of times when we're talking about the logic of algebra, none of those things really matter. It's when you're using the numbers that those start to matter. So we pick a point off of this axis that we care about, and we say that the variable x has a value of 2 meters, and we can again clarify that it's the variable that has dimensions of length without knowing what that number is, but once you put a number on that variable, you've got to know what the units are to know what that numbers means. So I always like to say variables have dimensions, they're more abstract. Numbers have units, that's much more specific. Clearly they're related to each other though, because you're only going to use certain unit systems to be able to characterize a particular dimension.